I'm Richard Gardner, Chairman of Farnborough Air Sciences Trust, and welcome to Farnborough, the original birthplace of the Black Arrow project, initiated by the Space Department of the Royal Aircraft Establishment. It's highly appropriate that I can speak to you today beside this amazing survivor, the original R3 first stage of the Black Arrow that exactly 50 years ago, on the 28th of October 1971, successfully placed the RAE's Prospero satellite into Earth orbit, where it remains today. This achievement was a first for the UK, combining a British designed and built launch vehicle and satellite, and represented a culmination of 25 years of UK space research and rocket programs, with the RAE playing an important role at all stages of development, which was shared with leading industrial partners. This world-famous research and development centre has been at the forefront of aeronautical and air science progress since the earliest dawn of aviation, in fact even predating aeroplanes with balloons and kites, before Samuel Cody successfully completed the first powered, controlled, manned aeroplane flight on the 16th of October 1908, just a few yards from this very spot. A full-scale replica of this flying machine stands facing the Black Arrow R3 first stage and highlights to visitors to the vast museum from around the world just how far science advanced so dramatically over the first 70 years of history. Over that momentous period, the RAE's dedicated engineers, scientists and technologists, along with test pilots and highly skilled mathematicians and other specialists, designed, tested and evaluated thousands of game-changing innovations, and by the 1950s, space research was high on the R&D agenda. From the mid-1940s, the need to expand knowledge on all aspects of rocket and missile development, as well as advanced air-launched weapons, focused attention on such subjects as special manufacturing processes, intensive materials and performance testing of air and space vehicles, rocket motors, and the establishment of new high-speed tracking data collection expertise. As this work intensified, initially to provide a new generation of rocket-powered missiles for military applications, the RAE coordinated the UK government's search in 1946 for a suitable testing range that would allow all the new experimental and prototype projects to be launched and evaluated free from land, sea and air traffic, and where classified trials could take place in safety and in a secure environment. Very intensive range activity was envisaged, so a full range of support facilities in a remote area would be required, including living quarters, comprehensive maintenance workshops, and both air and surface communications links. Such a test area would need to be huge in area, and Britain would need to be able to operate in a sovereign capacity, but in partnership with a trusted ally. Canada and Australia were obvious candidates, but the severe cold climate in Canada's wilderness areas ruled this out. The chosen location for the establishment of a vast new missile range was Woomera, Australia. This became a major UK-Australia joint project, and on the 1st of April 1947, Woomera, 400 kilometres north of Adelaide, became the site for the Western world's largest overland rocket range, covering 270,000 square kilometres, extending up into the northwestern direction, 1,850 kilometres towards the Indian Ocean. A whole new community was built in an arid desert, bringing in sufficient water. Itself just involved building a pipeline and storage for 12 million gallons to meet both human and launch site needs. The Australian partners set up a weapons research establishment at Salisbury near Adelaide to act as manufacturing and support base with an air link to Woomera, and RAE experts flew out and gradually expanded operations. Early work was undertaken by an RAE ballistics group which devised new instrumentation for data collection and reporting to assist the analysis of trials. Some of the first trials concerned the handling and delivery of large and heavy UK nuclear weapons destined for the new V-bomber force. Suitably trials-equipped RAF and RAE aircraft were deployed regularly to Woomera for these various trials. Other dedicated trials aircraft were permanently based there. An RAE missiles project group was also set up and was to become very busy over more than 30 years with UK missile trials. The space activity at Woomera required enormous investment in dedicated launch facilities, including special erection buildings capable of preparing the 104-foot tall Blue Streak, which was intended as the UK's silo-based nuclear deterrent delivery vehicle. And everything for a full-size launcher base had to be purpose-built, including the actual launch platforms, all the special assembly and hold-down locking devices, control rooms, tracking stations, operating and support crew facilities, and all situated in one of the hottest and most remote locations on the planet. After the UK abruptly cancelled Blue Streak in 1960, the strategic nuclear deterrent, which was going to be delivered by 70 rockets in favour of US-supplied Polaris submarine-based missiles, Blue Streak was re-rolled as the first stage of a new European satellite launcher, Europa, and this helped sustain some of the launch facilities at Woomera, while the UK brought forward a much smaller and lower-cost satellite launcher, Black Arrow. This needed more modest launch assembly and launch facilities, but had all the basic equipment and buildings in place at Woomera, to which others were added. A clean room became an essential element in the final testing and preparation of the satellites due to be launched by Black Arrow. As the UK launcher activity ended at Woomera with the cancellation of Black Arrow, Australia looked closer towards the USA as a partner in space activity. And in 1971, a major satellite tracking and ballistic missile early warning station was established at Naranja. The airfield and range facilities at Woomera continue, however, to this day for both UK and US trials and evaluation purposes. BAE Systems has carried out extensive trials of a family of autonomous unmanned air systems, including the Mantis and Taranis projects, supported by MOD and the RAF. Today, Woomera sees a new generation of flight testing for the Australian-designed and built Loyal Wingman unmanned aircraft being built with Boeing. By bringing the R2 and R3 surviving Black Arrow stages back to the UK, Skyrora is presenting an opportunity for a new generation to learn about these pioneering space vehicles and to inspire them to take a closer interest in space technology. And where better to see this than here at Farnborough, where it all started. I'd like now to introduce Dr. Graham Rood, who is the FAST curator and keeper of the massive archive we have here. Over to you, Graham.
Farnborough has been involved with rocketry since the closing stages of World War II, when German missiles in the form of Wasserfall, Foil Lily X5 and others were examined at RAE, and the British equivalents of Brakemine, Stooge and Lopgap were under development and experiment. These three missile programs eventually led to fruition. Lopgap led to the RTV series and finally Sea Slug, Stooge to the Fairy Fireflash control system, and Brakemine to the guidance system used on the Bristol Bloodhound. Now, armament had been set up at Farnborough in 1936, and due to the technical direction that missiles, predominantly in this case anti-aircraft missiles, were moving, armament was changed to controlled weapons, and shortly after to guided weapons. RAE set up a program to build 2 test vehicles to help understand the guiding principles of the weapon systems. That is, the structures, the aerodynamics, servo controls, guidance systems and propulsion. 2 early test vehicles were CTV-1 and RTV-1. Now, CTV-1 was used for a good deal of aerodynamic investigation, together with the development of free flight instrumentation and measurement techniques. It was UK's first beam rider and was also used in a command guidance role, and the beam riding work was done in close cooperation with TRE, who were responsible for the guidance aspects. RTV-1 was a larger vehicle used mainly on beam riding guidance research. A later version was used in a vertically launched role to study launch and stability problems preparatory to the Black Knight work. The CTV series culminated in CTV-5, which itself took various forms. CT-5 Series 1 was designed for aerodynamic measurements on coasting dart at high instances and therefore at high altitude, and CTV-5 Series 2 was used for kinetic heating. CTV-5 Series 3 was an upper atmosphere sounding rocket and was later known as Skylark, which had 441 highly successful launches. RTV-2 was designed for further work on liquid fuel propulsion and semi-active radar guidance research, and was later developed into the better known GPV. An interesting method of recovery from the sea at Aberporth range was developed for this vehicle. Now we come to Blue Streak. In 1955, a staff target for Blue Streak was issued, and RAE was primary R&D coordinating authority, and its initial task was to specify the amount of propellant to be carried, and thus the physical size of the rocket, and the accuracy of the guidance system. Then, in those days, the trajectory, boost phase, free flight and re-entry involved considerable amounts of calculation and analysis, all with limited knowledge of the shape of the Earth and the properties of the atmosphere. Static test firings were made at Spade Adam, and the first missile was being shipped out to Woomera in April 1950 when the project was cancelled. Now, though the cancellation of Blue Streak was a blow, many of the technologies being developed for the ICBM program were relevant to the Polaris program that replaced Blue Streak. On the 1st of January 1962, James Lighthill, the director of RAE, decided to bring all the aspects of space work together and form Space Department. Now, Black Knight was an experimental program designed to investigate the problems involved in a wide range of problems in the development of large ballistic missiles, not the least of which was those arising from the control physics of flexible, high mass ratio vehicles using swiveling jet steering. Detailed design was started in 1955, and the first proving flight took place on the 7th of September 1958 and the next in March 59. Data on head re-entry physics and radar signatures during entry were part of the 22 successful Black Knight firings between 58 and 65. The program produced vast amounts of relevant data for the ballistic missile deterrent program and a great deal of NASA manned spaceflight shots. Finishing in 1965, it was one of the most successful space programs of its time. Black Prince was then proposed as a satellite launcher based on Blue Streak, first stage, a Black Knight second, with a 1,750-pound satellite launched to 300 nautical miles. However, other RAE studies, which were in progress at the time, revealed that the three-stage rocket launch from Woomera could achieve the desired result, and Black Arrow was born. Started in 1964, it was limited to a cost of 10 million, not a lot for a space program. The results have been described earlier in the conference by Doug Millard and others, and the result was the only complete launch of a UK satellite, Prospero, by a UK launcher, R3. The other launcher of note was the Falstaff series of experiments, which was a sounding rocket used during the 1970s as part of the Cheveline program to improve the penetration characteristics of the Polaris nuclear missile. Launched 8 times between 69 and 79 at Woomera, it failed only once and has the distinction of being the largest UK rocket with a solid booster ever launched. Now we move on to satellites, and as Brian Day notes in his excellent history of RAE Space Department, satellites without orbits would be like Hamlet without the Prince of Denmark. And whilst the USA and Russia fought out the battle of bigger and more complex satellites, the UK, through RAE, was to beat the superpowers at their own game in one important area. This was to observe the first 2 Sputniks and to accurately compute their orbits and to deduce reliable values of the geophysical parameters responsible for any of the important perturbations of orbit. This was headed by 2 exceptional people, Desmond King Healy and Robin Merson. A highly successful program, and FAST holds the personal papers and documents, including all the documents of praise from the Russians of Desmond King Healy. Now, in 1960s, satellites became an increasingly important component of signals intelligence, and only 2 countries utilised satellites for signals and military intelligence, the United States and the Soviet Union. So as a consequence, the United Kingdom created Skynet as its own military communications satellite. And whilst it provided secure and encrypted facilities for the British Armed Forces, the largest user of the satellites was the Government Communications Headquarters, GCHQ, who were responsible for more than 80% of the communications traffic. And that traffic was subsequently returned to the United Kingdom. Now, these Skynet 4 satellites had only a few similarities to the earlier generations. The cylindrical body of the Skynet 1 and 2 was replaced by a large square body housing antennas with deployable solar cell arrays. This marked the technological improvement from spin stabilisation used in the early cylindrical satellites to 3-axis stabilisation using momentum wheels and reaction wheels controlling the satellite gyroscopically. Now, Ariel 4, known pre-launch as UK4, was a British ionospheric research satellite which was launched in December 1971 aboard an American Scout rocket. It was designed to meet one scientific objective, which was to study the interaction between high-energy charged particles and electromagnetic radiation in the upper ionosphere and magnetosphere, making it the first mission-oriented satellite for the UK. Ariel 4 decayed in orbit in December 1978. A further area where RAE had a significant input into space exploration was in the field of electric propulsion, and that came in the form of the ion thruster. Of the RAE, the earliest successes of the initial tests with the T1 thruster resulted in the design of a new device, the T2, for which a 10 centimetre beam diameter was selected to provide a thrust of 10 millinewtons with a beam accelerating potential of 2 kilovolts. Using experience gained from the T1 and the T2 programs, coupled with the plasma and ion beam diagnostics carried out at Culham, RAE then designed the T3 thruster, which was constructed in industry in 71, was replaced a year later by the T4 and then later by the T5. This 10 centimetre T5 ion thruster has recently flown successfully on ESA Gochi mission, and the 22 centimetre thruster was selected for the ESA BioBepi Columbi to propel a spacecraft to Mercury, and it is being qualified under ESA sponsorship for the Extended Range Communication Satellite Platform. Now, the RAE's long history of involvement with space design, development and program management is now encompassed in Qinetiq and will hopefully continue way into the future.
Having shown you some of the background to the RAE Space Department's activities, we'd now like to show you a film which is actually silent, but we put captions to it, showing you some of the preparation work and activity down at Woomera, which was connected with the launch of Black Arrow. We hope you enjoy the film.